let's talk about high school math. For a lot of us, it was a class we had to take. But what if I told you there's a hidden story, a secret architecture, hiding in plain sight in your old textbook? You ever have that feeling in class? One day it's triangles, the next it's all about x, and then suddenly you're talking about the odds of rolling a 7? It feels completely random, right? Like someone just threw a bunch of ideas into a book? Well, it turns out it's not random at all. Your math education is actually a lot like a massive building project. Every single topic from geometry to algebra is a block that's been carefully placed on top of the last one. It's a story of construction. So today, let's be the architects and see how this thing was built, right from the ground up. Every building, every single one, needs a solid foundation. And in the world of math, that foundation, it's just numbers. Simple, basic numbers. It's the very ground that everything else is built on. Okay, imagine we have an empty bag. First, we throw in the numbers we use to count things, 1, 2, 3, and so on. Those are the natural numbers. Then we add a really important idea, 0. Now our bag has the whole numbers. Okay, what about the other side of 0? Let's toss in all the negatives. Now we've got integers. But look at all those gaps between the numbers. We can fill those in with every fraction you can think of. 1/2, 3/4, you name it. Those are the rational numbers. And believe it or not, there are still a few tiny, weird gaps left. That's where numbers like pi or the square root of 2 fit in, the irrationals. You put them all together and our bag is totally full. We have the real numbers, a perfect unbroken line. That is our foundation. So, our foundation is poured. What's next? You need blueprints, right? Before you can build, you gotta have a set of rules for how space and shapes work. And for that, we need to go way back to an ancient Greek mathematician named Euclid. Euclid started with things that sound almost poetic. He defined a point as something with no part. It's just a location. A line is breadthless length. These aren't complicated formulas. They're simple, core ideas that everyone can kind of feel and agree on. These are the Lego bricks for the entire universe of geometry. Now, to build with those bricks, Euclid laid out the rules of the game. He came up with 2 types. First, you have axioms. These are just obvious truths for all of math. Like, if 2 things are equal to a third thing, they must be equal to each other. You don't have to prove it, it just is. Then you have postulates, which are basically the same deal, but just for geometry. For example, you can draw a straight line between any 2 points. These are the fundamental, unprovable truths that the rest of our building will stand on. All right, foundations in, blueprints are approved. Now the fun begins. We get to start putting up the framework. And to do this, we're going to use 2 of the most powerful tools in the box: geometry, the language of shapes, and algebra, the language of symbols. So let's make this real. Imagine a triangular park. You can walk around the outside and measure the sides. No problem. 40 meters, 32 meters, and 24 meters. Easy. But if you want the area, you probably remember the formula, right? Half the base times the height. But what if you can't measure the height? How are you supposed to figure that out? Are you stuck? Nope, not at all. This is where algebra swoops in to save the day. See, a brilliant mathematician named Heron figured out a formula that lets you find the area using only the side lengths. Look at it, it's pure algebra. It's a recipe of symbols that solves a physical, geometric problem. All of a sudden, you don't even need the height anymore. You just follow the recipe, you plug in the numbers for A, B, and C, do the math, and boom, you get a perfect, precise answer. 384 square meters. That's the magic right there. We're using the abstract power of symbols to figure out something real about the world of shapes. For centuries, geometry and algebra were like these 2 separate, powerful kingdoms. They were both super useful, but they didn't really talk to each other. Then, one guy had a revolutionary idea, an idea that wasn't just a bridge, but a map that proved they were living in the exact same world all along. And the person we have to thank is René Descartes. The story goes that he was just lying in bed, thinking. He was watching a fly buzzing around on the ceiling, and it hit him. He could describe that fly's exact position at any moment with just 2 numbers. Think about what a huge deal this was. Before Descartes, you had geometry over here, the world of things you could see, pictures of circles, triangles, squares. And you had algebra way over there, the abstract world of x's and y's and equations. 2 totally different languages. But what Descartes invented, the Cartesian plane, was like a universal translator. He just laid 2 number lines over each other, an x-axis and a y-axis, And suddenly, every single point in space had a unique address, an x, y coordinate. This was the moment everything changed. Now, a circle wasn't just a round shape, it was also an equation. A line wasn't just a straight mark, it was y equals mx plus b. The two separate worlds were finally, beautifully, one. Okay, so our incredible mathematical structure is built. We've got our number foundation, our geometric blueprints, our algebraic framework, and a map that connects it all together. It's really impressive. But what's it actually for? Well, the final step in your math education is learning how to use this amazing structure to make sense of the messy, unpredictable, and often confusing real world.
One of the first tools you're given is statistics. The world is just drowning in data, like your monthly expenses. It can be overwhelming. But statistics gives us ways, like a simple bar chart, to take all that chaos and turn it into a clear visual story. In a second, you can see exactly where your money is going. It creates order out of noise.
But describing that data isn't always so simple. Check out this story about two students, Hari and Mary. They both take 5 tests. Mary works out her average and gets an 8.4. Hari gets an 8.2. So, case closed, right? Mary did better. But hold on. Hari says, yeah, but my middle score was a 10 and yours was only an 8. So, who's actually right? See, this is why math is so cool. It gives you different tools for different jobs. What we usually call the average is the mean, but it has a weakness. One really high or really low score can throw the whole thing off. The median, on the other hand, is just the number smack dab in the middle when you line them all up. It doesn't care about crazy outliers. It tells you about the true center. And there's even a third tool, the mode. That's just the number that pops up most often. For Hari, that was his score of 10, which he got 3 times. This is incredibly useful in the real world. A shoe company doesn't really care about the mean shoe size. They want to know the modal size, the one they sell the most of, so they know what to stock up on. So statistics is amazing for understanding what's already happened. But what about what's going to happen next? For that, you get the final tool in the kit, probability. This is the part of math that lets us literally measure uncertainty. It got its start from people trying to win at games of chance, and now it powers everything from your weather forecast to the stock market. And there it is, the whole story. It's not a random collection of topics at all. It's a journey. You start with the very idea of numbers. You use them to lay down the rules of space. You build a framework with algebra, you create a map to link everything together, and then you use all of it to understand the real world. Every single piece builds on the one that came before it.
The whole point of this entire structure, from counting numbers to predicting the future, is to build one thing, understanding. It's a precise language we invented to describe the universe. So it makes you wonder, as our world keeps getting more and more complex, what's going to be the next block we need to add to this incredible building?